So is this? Okay. Okay, so hi. First of all, an apology. The titles should probably be the wrong way around, or the other way around. So this talk is more about this formalization of some syntactic properties of the modal mu calculus that I've been working on. And one of the nice things that fell out of that was, it involves some things to do with rational codata types. So I'm assuming that not too many people will be familiar with the modal mu calculus. So I'll start by talking about what that is and this construction called the closure, originally due to Fisher and Ladner for a different modal logic, but then brought into the mu calculus by Dexter Cozen when he introduced that. I'll briefly go through the sketch of the proof for the properties that we proved, namely that the closure is finite. There's a lot of gnarly details, so I will try and skip that and keep it high level. And then at the end, I'll narrow in on what already a question. Hi, Jake. Oh, yeah. Oh, shit. Is that any better? No? Worse? Is that? I better just do that. Okay. 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 So the modal mu calculus is an extension of the basic modal logic K with fixed point operators. So what is K? Well, it's, where's my laser? It's propositional logic plus the box and diamond modalities and then plus fixed points. So I'm going to commit a crime against logic talks and not talk about semantics to start with, which is not great, but we don't have too much time. So the most intuition that I can give without going too deep into that is that this is used for model checking. So you have some Kripke structure, which is sort of a graph, where each node has a model of propositional logic, and then the modalities let you reason about properties that might be true at all of the immediate successor nodes, or at least one of them. And then the fixed points let you extend that to then talk about potentially infinite behavior. What's most interesting to us here, though, is that these fixed points are variable binders. And also, yeah, the syntax is strictly positive. I'm going to skim over that. The key operation on the mu calculus that we care about here is so-called fixed point unfolding. So don't worry that I'm not telling you about the semantics, because the reason that's fine here is that this operation kind of encapsulates what the semantics of the fixed point is syntactically. So basically, if we have some fixed point operator, say mu x phi, then its unfolding is phi with this now free x substituted for the entire nu x phi. And this is a semantic equivalence. So this is how you kind of reason about what a fixed point formula means. So if we have one here as an example, mu x p or diamond x, then if we do one unfolding, then that says either P is true here or there exists an immediate successor where E is true. And then you can unfold this E of P again and say either P is true here or it's true at one of the successor states, or it's true of one of those successor states, and so on and so on. So this is the eventually predicate on P. Okay. And then what is the closure? This is the statement that we're formalizing here is that this construction is finite. So what is this construction? Well, if we have a formula, then we... Okay, yes. So the closure is the smallest set that contains the formula you're looking at and is closed under for the propositional and the modal parts of the logic, taking direct subformulas. And then if you have a fixed point, then you take the unfolding of that. So if you start with some phi, then if phi was modal, then you take its immediate successor and so on. And this gives you a nice sort of natural graph structure. And it's almost nice for implementing just directly as a recursive function. You could do this in something like Haskell, but the trouble is if you want this to be, if you want to know this is terminating, well, this last line is a problem here, right? Because this substitution here, this unfolding, is going to make the formula larger. It will eventually terminate, because eventually when you get to the variable x that was substituted here, well, it's being substituted for this mu x phi, which was already in the closure. So you will eventually loop back, but that's kind of hard to reason about. So when Dexter Cozen proved this originally, the technique he used was to define an alternate version of the closure that relies on this so-called expansion map that I'm going to try and not talk about too much. And then by some sort of hand-wavy-ish paper argument, says, yes, we do induction and it's all fine, it's finite, it's easy. But the trouble is that argument, well, this whole time I've been using variable names and it's been kind of high level on paper. It doesn't really work so nice as that if we're in a proof assistant, excuse me. So whenever we need to, yeah, so the trick here is whenever we go under a binder, your induction hypothesis changes, and then trying to do any kind of direct proof like this is really hard. So what we're doing instead is we do implement that previous definition of the closure I showed you directly. So we generate a non-well-founded co-tree from that. So just an infinitely descending tree that we kind of ourselves know is going to eventually repeat and loop, but we need to prove that. How do we prove that? Well, we also implement this alternative definition that Cozen gave, which is inductive and it is finite by construction. We implement this as a so-called sort of tree with back edges. So this is an inductive data type that I'm going to show you, and this is what I'm calling rational trees, where it's a tree with variable names, essentially. And that's not a new technique, but I'll get to that in a second. And then you can define the unfolding of such a tree with variable names to a non-well-founded tree. And then you get a notion of bisimulation between these two things. And then you can transport the correctness proofs from this first infinite tree where they were easy to prove over to this tree that's finite by construction to obtain that this one that you know is finite really also is the closure. So now the crime against talks is the just pages of code. So, oops. So this is our non-well-founded trees. This is a pretty standard presentation. So we have this kind of mutual co-inductive inductive thing going on here, where you have some X that you're storing, and then after that you have a label of either leaf where we stop, or you have a unary node. So this represents it being one of the modalities, box or diamond, or you can have a binary node, so that if that was an and or. And then you have another kind of unary node for mu and nu. And this works nicely, so we can define the closure directly to one of these, just directly from the definition, and it's easy. But then how do we prove that it eventually loops? Well, we have to get a little more complicated now. So the key here with these rational trees, the reason you might even think to do this is if you think about what's going on with any syntax of binding, right? What do variables tell you? You can think of a variable as sort of being a pointer back to its binding site, which if you combine that with the scope, lets you sort of infinitely traverse a term. And then as soon as you get to a variable, as long as you have a scope handy, that scope tells you what its binder was. So you can then sort of go back up there. Yeah. So the way this is set up, we have, again, a kind of mutual structure where we store an X and then we take a step. And then at any point, we can also say, this is a variable. So we're doing well-scoped the Brown indices, kind of standard stuff. We need to prove a lot of standard properties about this involving substitution and so on. And in fact, if I skip back to somewhere too far, yeah, this expansion map here is, I'm skipping around, sorry. So this unfolding here that I said was very important, this is a substitution. So we need a bunch of sort of standard properties of substitution in this syntax of binding, but that all falls out with not too much trouble. The expansion map is where it gets annoying. This thing is more like the kind of maximum instantiation of all of the fixed point of all of the free variables. So you do those one at a time. The way that interacts with the unfolding gets quite tricky. But yes, at the end of all of it, we can, so if we have one of these rational trees, then we want to be able to turn that, we want to be able to unfold that to get the non-well-founded tree. So that's not too bad. You need to say what the head is, and you need to say what the subtree is. So we can do this again, kind of inductive, co-inductively. Co-inductive, inductively. Yeah. So we reach a variable. This is where we have to inline lookup into the scope. So it's inline to make the termination checker happy, but basically you traverse your rational tree, and if you see, okay, I reach a and node, then that's going to be copied over in the non-well-founded tree. And then the only difference between the two of them is in the rational tree, you might eventually reach a variable, in which case you're traversing this, or you're building up this scope as you go with, which is a telescope, right? It contains all of the binders that you've gone past. So whenever you reach a variable, you then need to look that variable's binder up in the scope so that you can continue. And you can keep doing that infinitely because this is co-recursion, right? So you just keep going, and every time you reach a variable, you jump back up, and you just keep following this loop like that, and you build the infinite co-tree. And then from there, we need to then prove by simulation between this unfolding and the co-tree that we had originally, which is painful. And I'm not going to show too much of that. But what we get in the end after going through all the pain is we do get such a bisimulation between the easy to prove correct co-tree and the unfolding of the intrinsically finite one. And then we can show that you can transport the correctness properties that we had for the infinite tree along that bisimulation to the through the unfolding, rather, to the sort of equivalent version of what those properties would look like for the finite reconstruction tree. Yeah, one thing I skimmed over a little bit. This presentation of rational codata as syntactic binding, not new. So this was introduced by Neil Gani, Makoto Hamana, Tarmo Stalu, and Varmo Vene quite a long time ago. Yeah, I'm not sure what else I wanted to say about that. But yes, so this was also originally sort of pitched as a work in progress, and it did only come together last week in the end. So these two statements are proven now. There's probably more work to be done where, like, yes, so now we know that this intrinsically finite thing is the closure, but it's not the tightest size bound that it could be, right? Because this is a tree where you might have duplicated data in one branch versus another. So there's work to be done, and dealing with that is something that Gani et al. Did deal with in their paper. So that shouldn't be too bad. The reason that I wanted to talk about this at types in the first place, and it's kind of a shame that I ended up structuring the talk with this, but I suppose, is this rational codata stuff. Even though it's not new, it seems, as far as I can tell, to be kind of folklore-ish. Like, it was introduced by Neil and Makoto and Tarmo and sorry, those people. But yeah, more could be done here. It's an interesting avenue to look down. Sorry, I'm rambling now. So I will finish up there.